I actually prepared a Beamer talk, but Tyrone kind of bullied me into giving a chalk talk instead. It's all here, though. So I'm going to actually talk about two quite different things, but they're interrelated a bit. So first, they'll start talking about small volume hyperbolic three manifolds with paying special attention to the orderability of their fundamental groups. I think there's an interesting story there. And then I'll introduce the concept of order preserving braids. So first of all, goodbye, Millie and Meyerhoff. The closed hyperbolic three manifold orientable of minimal volume is the so-called Weeks manifold, which has come from 5/1, 5/2 surgery on the on this link. And interestingly, it's been shown, Nathan Dunfield and Danny Caligari showed that this group is not left orderable. Let's call this Weeks manifold W, not left orderable. I believe you actually showed us not even circularly orderable. So that's interesting fact about that small closed hyperbolic manifold. Now, what about ones with cusps? Well, if we have a one cusp three manifold of minimal volume, Meyerhoff and Cow so that they're for one cusp orientable hyperbolic three manifold of minimal volume. There are two examples. It's either the figure eight complement or its sister, which can be gotten by 5/1 surgery on one component of the Whitehead link. It happens that both of these manifolds fiber over the circle, and well, a general observation is that well, they both fiber over S1, and there's a result regarding orderability. For example, a figure eight complement, this group is bi-orderable, and that was shown by Bernard Perron and myself some years ago. And let me give the general setting for this. If X fibers over S1, we can regard X as the fiber across an interval where Y1 is identified with f of Y 0 for sometimes called monodromy, homeomorphism F. Now, when is this going to be bi-orderable? Well, let's consider, suppose I1Y is a free group rank, finite rank. We show that if you look at the abelianization, so that goes from Zn to itself. If this has all eigenvalues real and positive, I1x is bi-orderable.
Does that work for every free-group automorphism or just one that comes from the circle?
Well, if you have any free group automorphism, you can define a corresponding fibration. And yeah. And a partial converse of this is due to Adam Clay and myself. And that is if I1x is bi-orderable, then at least one eigenvalue of F abelian is in R plus. I'm kind of working into a corner there. So in the case of the figure 8 complement, this can be represented by a matrix 2, 1, 1, 1. This has eigenvalues 1/2 times 3 plus or minus √5. Indeed, those are real and positive, so therefore bi-orderable. For its sister, it's the negative of this. So all its eigenvalues are minus, well, 1/2 times minus 3 plus or minus √5. So it's not bi-orderable. They're both negative. Any questions so far? Now to look at more cusps, I'm going to start talking about orderable braids. So this is the second chapter of my talk. First of all, let me point out that free groups are bi-orderable. There are many ways to do this. So let's say F is a finite rank. I'm not going to put a subscript because I'm going to talk about the lower central series. That's what LCS stands for. So let F0 equal F and Fn be generated by commutators of Fn minus 1 with F. This defines actually normal subgroups. And it has a property that the intersection of the whole bunch is trivial. And also the successive quotients, Fn mod Fn minus 1, is pre-abelian finite rank intorsion free. I guess that's what I meant, pre-abelian. So each of these can be given an ordering. And if you choose an ordering for each of those, you can define the positive cone by looking at the sequence. So choose an order, a bi-order for each of these successive quotients. And then call, if you have F in F, call F positive in the last n for which little f is in Fn. If F is not the identity, it'll die somewhere. You take the last one, then F is the class of F is positive in the chosen order of Fn plus one. So this is one class of orderings of the free group. There are many, many others, but there's already uncountably many of these. And okay, now what does this have to do with braids? I'm running out of chalk. The okay. There's an important connection between braids and automorphisms of the free group. It's an Artin representation that takes the n-strand braid group into the automorphisms. Now I'll use this Fn, not for, well, F is rank n free group. It's gotten by observing how the braids act on a punctured disk. For example, sigma 1 interchanges these 2 points, little twist, and that induces an automorphism of the punctured disk. It sends well, sigma I takes xi to xi plus 1, xi inverse, xi plus 1 goes to xi. You can see how this is in case I equal 1. And xj goes to itself if j is not in I plus 1. And I'll call a braid order preserving if its associated automorphism preserves some bi-ordering of the free group. Some definition. Order preserving. Let me call this action, since we read braids from left to right, I want them to act on the right. So X goes to X beta, where X is in the free group. And then we have that X beta gamma is X beta gamma. It's just nicer to have a right action rather than usual functional notation on the left. So braid is order preserving if there's a bi-order of the free group such that x less than y implies x beta. Why did I introduce this funny concept? Well, we'll see that it has to well, one reason is proposition beta is a braid, an end braid defined, I'll call it the braided length of beta to be usual closure together with A, which is the braid axis. So a picture of that would be, here's the braid, and here's the curve. So it's a link with at least 2 components, depending on the braid, and they need more than 2 components. Then beta is order preserving if complement of that link has fundamental group by order. Because the fundamental group of the
Apologies.
the fundamental group of the complement is really pi one of the mapping cylinder of using that, you include that this will be bi-orderable if this preserves some by ordering and conversely. So that gives you a nice criterion for checking when the complement of link of a certain form is a bi-orderable group. That's great. Because if it were, remember sigma I takes xi to conjugate. If it were, and suppose we have a xi is less than xi plus 1 with the ordering. It's not, then I can take the reverse ordering. Can I take the microphone on? Yes. I'm annoying myself by talking. Going down that way. Okay. So if this is less than this, that would imply that. That would imply that this is less than that. But now, a bi-ordering is conjugation invariant. That would imply that xi plus 1 is less than xi. Conjugated. Oops. This by xi, yeah, same thing. And then that contradicts our original assumption.
When I mute it,
Okay.
so,
I'm going to actually do a slightly more interesting sigma 1, sigma 2 is not order preserving. So this acts on P3 or Pn for n bigger than both 3. So what's the action? X1 goes by 2, goes by sigma 1 to X1. I'm still causing an echo even that one. Here's the action of sigma 1, sigma 2 on the 3 generators of the 3 food on X1, X2, X3. Now, if the consumants order preserving, so assume order preserving with X1 less than X2. Well, if X1 is less than X2, then X2 must have been less than X3. But also, if X1 is less than X2, this must be less than that. X1, X2, X1 inverse. Oh, sorry, X3. We have X1 inverse. X1. That's from that. Now, if you conjugate by X1, that implies that X2, X3, X2 inverse less than X1. Now I can't really conjugate anymore, but remember X1 was less than X2. Now that implies that I forget about the middle one, conjugate by X2 and I get the X3 is less than X2. That's a contradict this. Now let's see if I can convince you that X1 squared X2 is order preserving. Well, consider this. Well, let me first remark proposition. Pure braid is order preserved. So suppose pure braid is one for which the associated permutation is the identity. So that means that in regroup on F1, which is it acts as the identity. And then we note that it also then proved that in fact, so it acts as the identity on all these lower central quotients. So any LCS ordering will be preserved by beta. It preserves. So here's a say sigma 1 squared. Here's a braided link. So this is order preserving because it's a pure braid. You can in fact notice that I1 of the complement of this is I1 is regroup of two generators across the energy. So I'm going to do a disk twist on this. And then I get that right. Where I should have kept my beaver talking. Now this. So that. So I'm going to twist along this followed by this curve. And now I see that this is the braided length of sigma 1 squared. This is braided length of sigma 1. I've got this backwards. Sorry. I got that wrong too. So these two lengths have homeomorphic complements. This has bi-order fundamental group complement, so this does as well. So therefore, sigma 1, sigma 2, sigma 1 is order preserving. Also, if you observe here, if you have an order preserving braid, any conjugate of it will also be order preserving. So also, this conjugate sigma 1 squared, sigma 2. Order preserving. Similarly, we can show that sigma 1 squared, sigma 2, sigma 3 up to sigma k, this representing or MK. With a few more times. And we'll see. Now let's get back to hyperbolic three manifolds. According to Ian Egal, mineral volume, orientable, two cusp hyperbolic three manifolds of minimal volume. It's one of two things. It's either the Whitehead link complement or the complement of a -238 pretzel link. Now, proposition the Whitehead link complement as bi-orderable I want the complement. But I claim that not so. For -238. So again, in the two cusp case, we have two minimal examples. One of them is bi-orderable I1, the other one is not bi-orderable I1. It is left orderable, but not. Any link complement is left orderable I1, but not bi-orderable. Let me just verify this, -238 complement. Automorphism 2. That. That looks like the sigma 1. Huge. Sigma 2. Sigma 3. And the right number of strings. Yeah. Now you gotta just check this by hand. I'm not gonna do that. But then we check that this grade. Now we're into some reserving. By contradiction, as we have done with a couple other examples. Again, I won't go through that. It's rather complicated. Now, I'm going to skip 3 cusps for the moment. Let's look at 4 cusps. That was shown by Yoshida. Minimal volume cusp. Interval hyperbolic. 3-manifold. Automorphism to complement of this. I claim that orderable group bi-orderable. See that by realizing that as coming from a braid, the preserving effect. Same as with this guy is automorphic to that sigma 1 minus 2 sigma 2 squared. Right. You have to do a little disc twisting in there to see that this is a 4-component length. And so is that, and you can actually check that their complements are homeomorphic. But notice that this is a pure braid, so this is order preserving. That means that I1 of this complement is order preserved is bi-orderable. There's similar results. I won't go through it for 5 and 6 cusps, although they are. No. Yeah. Maybe I'll just finish by some.
Dale,
Yeah.
what do you mean by similar results? I mean, in the sense that we don't have minimum volume by the cusp.
Yeah, we don't know. It's conjectured that for 5 and 6 cusps, there's similar chains like that that give them minimal volumes. But I don't think that's really known. But anyway, their groups are also bi-orderable. There's the 3 cusp case was also conjectured. It's conjectured. Its complement is minimal volume 3 cusp, et cetera. I don't know whether this has bi-orderable fundamental group complement or not. It's this is I1 complement bi-orderable. If and only if the braid sigma 1 squared sigma 2 inverse order preserving. And I don't know the answer to that, whether this is order preserving. I've tried to show that it's not, but it more likely is because I couldn't prove it wasn't. Let me just now conclude with some remarks about this class of order preserving braids. It's a subset of BM, contains pure braids, so it's a fairly large subset. It has ordered at least over n factorial. Is normal conjugate of any order preserving braid. So let's let OPN BN be the order preserving. And notice that the pure braids I and OPN is normal. It is not a subgroup. Well, for n equal 2, it is Pn equals Pn. But then figure n equal 3, it's not a subgroup. Because we noted that sigma 1 squared, sigma 2 is P. So is sigma 1 minus 2. But if you multiply them, let's get sigma 2. Orientation preserved. But we did see that sigma 2 is a product of 2 orientation preserving braids. And now all sigma 2 equals the product of 2 orientation preserving braids. And now all of the braid generators are conjugate to each other. That's easy to see. So also, since the conjugate, all sigma I are a product of 2 orientation conserving braids. Just take the appropriate conjugates of those. And therefore, OPM generates it's not a subgroup, but it's big enough to generate the whole group. Okay, thank you. I think I'll end there.
Thank you. And we have comments.
Every one of these examples you gave, you put all cusps or conjecturally minimal cusps. It was clear, well, you managed to show them as a braided link.
Yeah.
Is this expected to always be the case? Okay, this will happen.
It happened, yeah.
Okay.
Well, it's not in the one cusp case, it can't be because of braided link is instead at least 2 components. So, yeah.
No more questions. We have